Good afternoon, class. So yesterday we ended up looking at how a single charged particle emits electric fields, positive charge emit fields that are radially outward, and negative charge emit fields that point radially inward. So we're going to see what happens when we have more than one charge interacting. Now, a real interesting now, the thing for us to note here is that these electric fields, they are vector fields. And as we've covered in the very beginning of our class, when we started with vectors, is that any two vectors of the same type acting on the same object or in the same place, you can find the end resultant vector by taking the vector sum. So I'm going to show what's going on here by showing the superposition or the addition of these two electric fields acting at one time. So let's imagine our situation with two positively charged particles. I'm going to use two colors here so everybody knows, so just be aware of that. Let's see, I'm going to try to lighten it up. Maybe I'll make it really fine. So the first one that I'm going to do here in pink is showing the electric field of each of these charges individually. Oh shoot, sorry, that's a little sloppy. But it's showing the electric field of each of these charges individually. And so you can see it's radial, and these would be pointed outward. And same with this one. It's also going to be radial, pointed outward. Now, what is going to happen here is in blue, I'm going to draw their vector sum. Let's start in the middle. In the middle, it's easy to tell. You can have the arrow from one heading to the right and the arrow from the other heading to the left. These arrows are interacting, and right in the middle here, we're going to notice that they should cancel out. There should be no field at that point. So I'm not going to draw any line there. What's going to be happening? And up here at the top, we notice that, oh, one is pointing up to the side, the other one's pointing up to the side, that the field is pointed, again, straight upward. And so as we get in, and perhaps say if I was to moving in somewhere closer here, this field at this point is pointed this way. But from the other one, if we trace our way across, it's going to introduce a small bit that way. So the vector sum of these two fields, the vector sum of those two components, actually pushes this field a little bit out this way. And we're going to see that these fields, as we come in, as you get closer to the center between these two fields, they don't want to push inward because the inward force from both of them is interacting almost equally from each side as you approach the middle. And so we end up getting an interesting piece. You end up getting an asymptote right down the center where the field lines from either one are not going to interact, and they will begin, the field lines would begin approaching but then curve their way up. Now you can see it's getting a little sloppy. It's getting a little big in there, but hopefully you get the idea that in the middle between two positively charged particles, you'll have an asymptote where their field lines are going to be pushed outward. And everything that's happening is gets a little pushed outward. So you can see that the resultant field is almost the same, but one field on the charge on the other side pushes the fields out just a little bit because its own field lines are pushing up. And the only one that doesn't really change are the ones that are along the axis of the charges. So what we have here in blue, right? So take a look at what we have in blue. We have the electric field that is responsible for two positive charges. It looks kind of radially outward, but pushed as if, say, the charge on the right is providing an electric wind, perhaps, that's bending these field lines out. And the one on the left is doing the same for the one on the right. It's providing this, quote, electric wind that is pushing the field lines out. Hopefully that kind of makes sense. You see these bending field lines and the asymptote. Now, what should we expect to see with two negatively charged particles? Negatively charged particles are identical to positively charged particles, just symmetric in the opposite way. So instead of all of these field lines going radially out, all of these field lines are going to be going radially in, but they're going to be pushed a little bit. And so we're going to see a completely identical set of net field lines that have this bit of bend, right, coming straight up, but the further you get away, the greater the impact of the other one. And right in between the two, there's going to be another asymptote where your field lines are going to begin curving toward. And we should see a symmetrical thing around here. If you're like, Mr. Westgard, that doesn't look symmetrical, then yeah, I know I'm not that good of a drawer. That's okay. Suck it up. I mean, it's fine. You're getting the idea. That's what's important. So we see something looks almost identical to what we have with the positives, but instead of pointing outward, all of these arrows are pointing inward. Oops, that was the wrong way. Inward arrows. There we go. Inward arrows. And this is the beginning of our visualization of multiple particles. Just two particles here at a time. The goal is hopefully we'll begin to work further and further, getting more and more particles and be able to estimate and get a rough look of what the electric field would look like with multiple particles, but you never really need to worry about it more than one at a time. This trend of like particles have this kind of smooshing and asymptotic effect is going to be the same for all positive charges, even if there are other, or for all like charges, even if there are other charges around. If there are 3 or 4 or 5, we'll keep getting this kind of smooshing effect, and we'll always have lines of symmetry across an asymptote. So that's what we're going to be looking for, is these trends. Not specifically getting it exactly, but once we get comfortable with the trends, we'll be able to draw these with confidence. So let's take a little note here. Note our electric field lines, right? The electric field lines that we see, they point where a proton goes. Because the electric field lines are defined as where a positive charge would end up going. So I just use a proton, for example, because we all know protons are positively charged. And because this electric field is a force field, it's a vector. So as we saw here, when our fields started overlapping, we simply vector added them. We simply vector added them. Now, that's like charges, and we see, and hopefully we recognize that the positive to positive and negative to negative are symmetric situations, so we should see something similar. What happens when we have not a situation symmetrical to this? What happens when we have a positive and a negative? Oh, I'm going to do my two colors again. My positives radially outward, like this. and my negatives radially inward. So trying to go over in blue, let's again start with our simplest section. Let's take a look right in the middle here. See how the positive is pointing to the right, and then the negative is also pointing to the right? These two field lines are actually going in the same direction. If you were to add them up, it would simply be to the right. And so we actually get a net field that's going straight from the positive to the negative. They're additive in this case, not subtractive. And if we look, say, up here closer to the top, we would see that the positive charge is pushing kind of up and to the right, and the negative charge is going down and to the right. Well, if the right parts are adding together and the up and down parts are canceling, it'll end up going perfectly horizontal. And the same should happen in the symmetric case at the bottom. It's going perfectly horizontal here. And we'll actually notice that there is an axis of symmetry. So while these other two were asymptotes, this is actually an axis of symmetry. Which is a little different. Now, close to this charge, hopefully we remember that the electric field strength is kq over r squared. When r is really small, the electric field is really, really strong. So really close to this charge, the effect is almost caused entirely by the positive charge. The effect from the negative charge, it's a much longer r, not going to be as impactful. So it's going to follow almost exactly the same line. As it goes along, it begins getting pulled in by this negative charge and the field line until it reaches that point where they balance, and we have this perfectly horizontal line right on our axis of symmetry, and then the negative charge begins pulling in that field line until it begins connecting there. And so we see also a symmetric and equal thing happening at the underneath. Hopefully you can tell that, oh, a pattern begins emerging, and we will be able to estimate or approximate what this field looks like. Now, I'm not doing a very good job of drawing my curves. It's a little too blocky, but you can see that it begins making this kind of rounded figure where things are coming out of the positive and curving to go around to go into the negative. Curving to go around to go into the negative. And the only things where the only field lines that won't be able to make their way out of the positive into the negative are specifically the ones that are on the outsides of the charges going perfectly along this the axis that they lay on. So we get a little pattern like this where you can see if you follow the blue, it goes out of your positive charge and it curves around to go into the negative charge. Some of you might have actually seen something like this. This looks exactly the same as the magnetic field lines from a magnet. This actually has a particular name. This is called a dipole. It's called a dipole because it's di, to, pole, two poles, a positive and negative pole, much like a magnet has a north and a south pole, and those have this exact same field shape. So dipoles, like magnets or charges in this case, always follow this exact shape. And so that's a really nice thing. Again, so we can see our two fields interact. This time they seem to they merge together because they are working together as opposed to forcing each other apart. So when they were like charges, there was all that repulsion. They kind of pushed apart. Here, when they are attracting, they attract and they merge together. They make this dipole shape. Okay, so I hope that's helpful. We're going to work on visualizing these different types of fields and field lines when they're in different shapes or when they're in different configurations, when their charges are different. But if you know how like charges look and how a dipole looks, you can kind of mix and match. For example, if I had something that looks like this, if I had a positive, positive, negative, you can kind of separate it into pieces. Ah, it looks like in this section I have two positives. And sure, the negative is including some influence, but look how far away it is from this section. It means that we'll probably get this kind of pushing apart section that we saw before, right, with our two like charges. But over here, that's a dipole. So I should expect to see a dipole. And sure, while the positive charge at the far end is having a bit of influence, it's so much farther away, it's not going to have as much impact. So we notice, I like, oh, I should see dipole behaviors over this way. And bam, we did it. We already drew, so we have now drawn an approximation of the electric field of these three charges simply by using our patterns of the different charges and seeing how they interact. So hopefully that makes sense. We will practice this more. There will be more time for us to practice. We'll be using simulations to help prove this to us. But these patterns are what we're looking for. So you're looking for the like charges pattern and the dipole pattern when you're looking for multiple charges together and you want to draw the electric fields. So to bring it together, what's going on here? Can we also do these things numerically? And the answer is yes. And we do this the exact same way that we've been doing our forces. Is that, say I have the strength of an electric field midway between a 2 microcoulomb charge, so here's my 2 microcoulomb charge, and my negative 4 microcoulomb charge. And if they're 0.6 meters apart, midway, right here, this point right here has to be 0.3 meters apart for each one, 0.3 meters. How would I solve for this? Well, if this is object A and this one is object B, then you just treat them one at a time. A is positive. Positive goes radially outward. So at this point, it's pushing outward. Here's electric field A. B is negatively charged. Things go radially inward. So at this point, things should go inward. This is electric field B. So if I wanted to find my net electric field, I simply look at my electric field diagrams. Oh, A is this way, B is that way. They are in the same direction. So A and B should add together. And if I were to just crunch in the numbers, the electric field A, you know what, sorry everybody, I've been forgetting to put in my arrow hats because these are vectors for the electric field, not energies. So I'm going to arrow hat up, there we go. How do I calculate electric field A? Well, that's simply K charge A over RA, where squared, where R is 0.3. And then I would add K times QB over RB squared, where RB is also 0.3. And then you just plug in the numbers and calculator, calculator, calculator. I don't feel like doing it. But you get the idea. Take a look at this one. Aha, you have two 5.25 microcoulomb charges. And the whole thing is 0.4 meters apart, But I want to know what's happening at this one point. We're looking at 0.3 meters and 0.1 meters. Pardon me. 0.3 meters and 1.1 meters from this point. Again, label them A and B and treat them one at a time. A is positive, so it's going to be pointing out, electric field A. B is positive, so it points out from B, electric field B. And you might notice that I drew electric field to be much larger than electric field A, because they're the same size charge, and it's so much closer to electric field B, to charge B. And we know that electric field is related to the distance. The smaller distance, the greater the electric field. So that's why I made that one larger. If I wanted to find my net electric field, how would I do it? I would take electric field B and I would subtract electric field A. Why am I choosing to subtract? Because you can see from my diagram, these electric fields are going in opposite directions, so in opposite directions we subtract. Plug them into our formula. Note that RB would be 0.1, RA, so sorry, now I'm going to RB is 0.1 meters, RA is 0.3 meters. Punch that into your calculators, you should be able to get the result. But I'm not going to. You can do it. Now, this example is the same situation, but now things aren't in a line. The P is not directly in between the two. For the sake of ease, let's make this a 12 Coulomb charge, and let's make this one a -9 Coulomb charge. I realize I didn't actually label them, but we can do it there. How do we do this? Again, exactly the same process that we've been doing. This one's A, this one's B. Take a look. A is a positive charge. Positive charges push radially outward. Electric field A. B is a negative charge. Negative charges pull inward. So here's electric field B. For me to find my electric field, I need to add these, but I can't add them just normally because they're not in parallel directions. I have to do vector addition. So I'm going to go ahead and I'll do the calculations this time, I guess. Electric field A is equal to KQA over RA squared. So it's going to be 9 times 12 over, K isn't 9, K is 9 times 10 to the 9 times 12 over RA, which is 6 squared. 6 squared is 36. 12 over 36 reduces that to over 3, so this is going to be 3 times 10 to the 9. So we have 3 times 10 to the 9 newtons per coulomb is the unit for EA. EB is equal to KQB over RB squared. So we have 9 times 10 to the 9 multiplied by 9 all over 4.5 bracket squared. Let's see, 9 over 4.5 is 2, 9 over 4.5 is 2, so I'm left with 2 times 10 to the 9 times 2, so that'd be 4 times 10 to the 9 newtons per coulomb. And we have to remember, this one is directed downward, this one is directed to the right, and so my end result is if I drew it this way, four times 10 to the 9, 3 times 10 to the 9, and this is E net, or our net electric field. Net electric field is going to be 5 times 10 to the 9. I know that because 3, 4, 5 is a Pythagorean triple. So that's good. And if I remember right, this angle right here is 37 degrees. If you want, feel free to double check by taking the arctan of 3 over 4. Sure, the times 10 to the 9 you can include, but the times 10 to the 9 cancels out. But I'm pretty sure that's 37 degrees below right. Double check that in your calculators. I don't know. I like using this Pythagorean triple because it's easy. So that's it. That's what we got there for our electric field. That's not so bad. Now the next problem is, suppose you placed a proton right here at point P. What would the initial acceleration be? Well, I know I can find acceleration as a function of its force over mass. I don't have its force, but I can know its force as a relation of my electric field, because it's electric field multiplied by charge will equal my force. And so I can find, like, oh, my acceleration is just take my electric field, multiply by the charge, and divide by the mass. So for this, I just slap in my numbers, 5 times 10 to the 9, multiplied by the elementary charge of a proton, 1.6 times 10 to the negative 19, and divide by the mass of the proton. Now, you might not know that off the top of my head, and I'm going to do my best to remember it right. But if you don't remember it, that's okay. The mass of the proton is on your sheet of constants, so you don't even need to look for that so bad. 1.6 times 10 to the negative 27 kilograms, I believe. In this case, the 1.6's are canceling, so I'm going to have 5 times 10. Negative 7, negative 19, that's 8, so I believe that's times 10 to the 17. Again, feel free to double check my work, but I'm pretty sure I did that correctly. So 5 times 10 to the 17, this was acceleration, so this is meters per second squared. And I'm not done yet because acceleration is a vector. Which direction? It's the exact same direction as the electric field, because the electric field is the direction a positive charge or a proton would go. So at 37 degrees below the right horizontal. Woo. So I hope that's feeling good. We'll talk about that extension in a bit. But if we were to take just a recap, a gander at what we've done, we've kind of visualized the electric field, seeing how positive charges all push away from each other. And we can see that if you set up multiple charges, you can find the net force quantitatively by just finding find the net electric field by finding the electric field from each piece and adding it together. That's technically what we did to find these visualizations, and so we can just do the same thing but numerically in these cases. And this works for things in aligned, and this works for things that are not aligned. We just have to remember to use our vector addition. Hopefully you're feeling pretty good about that. Before we finish up, let's just take out a little extension. What would the electric field look like if you had a bunch of positive charges lined up together? So I have a bunch of positive charges all in a line that I've pinned down onto something, so they're not going to be moving around. So sure, they're repelling each other, but they're pinned, so they're not going anywhere. What's the electric field going to look like? Well, let's begin with just one. I'm going to draw the electric fields. Say this one is going to be pointing this way and that way and that way. It's pointing radially outward, radially outward. And so is its neighbor, radially outward, radially outward, radially outward. And so is its neighbor, radially outward and radially outward and radially outward, right? All of this. Now, what's going to happen? Take a look at what's happening right here. Right here at this point, this charge, I'm going to call it charge 1, is pointing straight out. charge 2 that sits just above it is pointing up and to the left, and charge 3 that's just below it is is down and to the right, and the other one's up and to the right. Well, down to the right, up to the right, they're equal distances apart. Up and to the right and down to the right, equal distances apart from that, means that the up and the down are going to cancel out, and the only thing that survives is to the right. The electric field from this charge is just headed to the right. And you could argue, but what about the ones above? What about the ones below? You can see that symmetrically, they should all cancel out. And this only has an electric field headed to the right. What about 2? Well, you can say the same argument is happening, but between 1 and 4, that you'd end up having pushing up and to the right and down and to the right, and it ends up all going to the right. And the same thing is 3 with 1 and 5. And through the process, hopefully you can recognize, oh, this is going to be the same across all of these charges, and only really begin to break down once you get to the ends where there isn't things to cancel it out. So what happens when you have a whole line of charges? What happens if we have a whole line of charges there, infinitely packed together, a whole set of positive charges, is you end up making a uniform field headed out in one direction. Now, by uniform, I mean it is all pointed in the same direction, and at any distance away from the plate of charges, right, any distance away from that set of that mass of charges all lined up together, it's going to be the same. As you move further and further away from the plate, it is going to die down and become less powerful, because we know that the electric field reduces the further you get away from the charge. So this is something useful. It helps get us a uniform set of charges. What we're going to be looking at later is what happens if you stack a set of negative charges on this side. Then you have the same pull situation, and you actually get a fully uniform field in between two parallel plates. So that so long as you do any science in between these two plates, you know at any point in the field, the electric field is going to be the same as any other point. And so this is how we can create uniform electric fields, is by the use of charged parallel plates. And we can affect the strength of the field by increasing or decreasing the separation of the plates, or by increasing and decreasing the quantity of charge on the plates. And this is going to be something that we are going to use quite a bit as we go later on. All right, so that's all for us today. You can look at 6.3, I believe, on your worksheet and give that a go. Unless 6.3 says energy. If it says potential or potential energy, then don't do 6.3. I forget. Wait, don't big deal. Have some good practice, everybody. I'll be back tomorrow. Have a good day.